Somewhere in the universe, there is a region so vast and so empty that it seems to break the rules of cosmic structure. The Boötes Void stretches across hundreds of millions of light years, with far fewer galaxies than astronomers ever expected to find in such an enormous space. It is one of the strangest places ever mapped, and its existence still raises deep questions about how the universe forms its larger structures. If mysteries like this fascinate the mind and calm the night, please like the video, subscribe to the channel, and settle in for the journey. The observable universe presents itself on the larger scales as a patterned expanse rather than a random spray of galaxies. Matter does not lie evenly across space. It gathers into a vast arrangement of filaments, which are long strands of matter, and walls, which are broader sheets where many galaxies collect together. Between these richer regions lie immense low-density spaces where far fewer galaxies appear. Astronomers call these broad, sparse regions voids. The name is simple, and the meaning is also simple. A void is not a perfect absence. It is a region where matter is present in much smaller amounts than average. In this large design, bright clusters of galaxies mark the denser knots. Filaments stretch across great distances like bridges, and the emptier spaces open between them with a scale that reaches far beyond ordinary imagination. This broad arrangement forms over deep cosmic time. In the early universe, matter is spread almost evenly, but not with complete smoothness. Tiny differences in density exist from place to place. Some regions hold a little more matter, and some hold a little less. As the universe expands, gravity slowly increases these differences. Regions with slightly more matter pull in more of their surroundings. Regions with slightly less matter lose material toward their denser neighbours. Over immense spans of time, these small imbalances grow into the largest known pattern in nature. The result is often called the cosmic web, a useful term for the giant network of clusters, filaments, walls, and voids that together shape the visible distribution of galaxies across the sky. From very far away in thought, the universe seems almost foam-like in structure, though no image can fully capture the scale. The richer parts are not solid surfaces, and the emptier parts are not clean cavities cut into substance. Everything remains made of space, gravity, matter, radiation, and time. Yet the contrast is strong enough that maps of galaxy positions reveal a striking architecture. Some parts crowd with galaxies by the hundreds and thousands. Other parts open into regions so underfilled that they seem almost abandoned. The Boötes Void belongs to this larger setting. Before it can be understood on its own terms, it must first be placed inside this greater order, because the emptiness that defines it is part of the same process that builds clusters and filaments elsewhere. The galaxies that human eyes and telescopes record are only one part of the picture. Ordinary matter, the material that makes stars, gas, dust, planets, and living bodies, traces the brighter features of this web, but it does not tell the whole story by itself. A larger share of matter exists as dark matter, which does not shine. It reveals its presence through gravity rather than light. Dark matter forms the deeper framework in which galaxies grow. Where dark matter gathers more strongly, galaxies tend to form more readily. Where dark matter is thinner and more spread out, galaxy formation is weaker. In this way, the visible map of galaxies follows a deeper invisible structure. Voids are therefore not simply places where a few bright objects happen to be missing. They are regions where the whole underlying distribution of matter is lower than average. Even this description remains only approximate, because the cosmic web is not rigid. It changes slowly as the universe ages. Matter continues to drift under gravity. Galaxies move within larger gravitational flows. Clusters grow by drawing in more mass. Filaments become the routes along which matter streams. Voids, meanwhile, tend to expand as matter drains away from their interiors toward denser edges. This does not mean that empty space pushes outward as if it were a wind. It means that, in a region with less matter, gravity pulls more strongly from the outside than from the inside. So material gradually leaves the sparse zone and joins richer structures. The emptier region becomes emptier still. In this quiet way, the large pattern sharpens. Seen across the observable universe, voids are not rare exceptions. They are a normal part of cosmic structure. Many voids are known, and they come in a wide range of sizes. Some are modest by cosmic standards. Others stretch across distances so large that they challenge ordinary language. The Boötes Void stands among the best known because of its exceptional scale and the surprise it caused when it was identified. Yet even its vastness is not separate from the overall order. It is one expression of a rule that acts everywhere on the grandest scales matter becomes uneven, and that unevenness grows. The same universe that creates crowded superclusters also creates broad underdense regions. Richness and sparseness emerge together. One cannot exist in its present form without the other. For this reason, the largest emptiness is not outside cosmic structure. It is inside cosmic structure. A void is part of the web, not a break from it. It does not mark a wound in space, and it does not imply that something has been removed by a violent event. It reflects how matter arranges itself when gravity works over billions of years in an expanding universe. The denser zones become easier to see because they fill with galaxies, glowing gas, and active stars. The emptier zones are harder to notice because they offer fewer visible markers. Their discovery depends not on seeing darkness directly, but on mapping where galaxies are and recognizing the unusual thinness of what lies between them. At this outermost scale, the Boötes Void is therefore best understood not first as a mystery, but as a location within a known cosmic landscape. The mystery comes from degree rather than kind. Astronomers do not find it strange that voids exist. They find it striking that this one becomes so large and so sparse. Its reputation grows from that contrast. It belongs to a universe whose largest map is already full of absence between concentrations of matter, yet even within that context it appears extreme. The eye, once trained to see the cosmic web, understands why such a region can exist in principle. The mind, when faced with its sheer extent, still pauses. This first view remains far from any single galaxy or survey. It stays with the widest setting, where the Boötes Void appears as one dark interval in a vast connected pattern. Around it, the universe continues with its threads, walls, knots, and open reaches. Nothing here is still in an absolute sense, but all motion unfolds slowly across spans so immense that change seems almost silent. The largest order of the cosmos emerges from small early differences and patient gravity. Within that order, dense regions shine with gathered matter, and broad, sparse regions open between them. The Boötes Void rests in that grand arrangement as one of its most striking underfilled spaces, defined from the beginning by relation rather than isolation, by the web around it as much as by the rarity within it. On the sky, the Boötes Void takes its name from the constellation Boötes, a familiar pattern of stars seen from Earth in the northern sky. The name gives a direction, not a container. Constellations are human-made regions on the sky, useful for locating objects by line of sight. They do not gather all their stars or deep objects into one physical family. The stars of Boötes are spread across very different distances from Earth, and the void lies vastly farther away than any of them. It simply appears in the same general direction when the sky is divided into named areas. In this way, the name joins an ancient pattern of visible stars to a modern map of deep space. Boötes itself is an old constellation, known for its large kite-like form and for the bright star Arcturus. Arcturus stands out easily because it is one of the brightest stars in the night sky. Its light reaches Earth across a distance small by galactic standards and almost negligible by cosmic ones. The Boötes Void, by contrast, lies hundreds of millions of light-years away. The difference is so great that the shared name can create a false sense of nearness if it is taken too literally. The constellation belongs to the near foreground of human skywatching. The void belongs to the remote large-scale structure of the universe. Their connection is only visual and directional, not physical in any close sense. This distinction matters because the sky seen by human eyes is a flat dome of directions, while the universe revealed by astronomy is three-dimensional. A constellation marks a patch on that dome. Within that patch, some objects are nearby stars inside the Milky Way. Others are distant galaxies far beyond it. Still others may be clusters, gas clouds, or underdense regions known only through surveys and careful mapping. The Boötes Void enters knowledge through this deeper three-dimensional view. It is not visible as a dark hole to the eye. No one looks toward Boötes and sees a clean, circular emptiness cut into the stars. The ordinary stars of the constellation remain in the foreground, while the void lies far behind them in the cosmic distance. Its approximate distance from Earth is often given as around 700 million light-years, though the exact extent depends on how astronomers define its boundaries and which survey method they use. This distance already places it on a scale where individual constellations lose almost all physical meaning and only directional meaning remains. At such depths, the Milky Way is a local detail. The local group is a small neighborhood, and even larger nearby galaxy concentrations become part of the foreground. The line of sight keeps extending outward into regions where galaxies appear as points, and the architecture of the cosmic web begins to dominate the map. The Boötes Void occupies one of these remote reaches, far beyond the stellar scene that first gives the region its name. To place that distance in thought, it helps to consider what a light-year means. A light-year is the distance light travels in 1 year. Light moves faster than any ordinary object known in nature. Yet even at that speed, it takes hundreds of millions of years for light from the region of the Boötes Void to reach Earth. The view received today therefore belongs to a very ancient cosmic time. The void is not being observed as it is in an immediate present shared with Earth. It is being observed as it was when that light began its journey across the expanding universe. This is true of all deep astronomy, but in such distant large-scale structures the time depth becomes especially striking. Looking farther also means looking earlier. Even so, the Boötes Void remains part of the observable universe in a fully ordinary sense. It is distant, but not near the horizon of what can be seen with modern astronomy. Many galaxies are known at far greater distances. What makes the Boötes Void memorable is not that it is the farthest known structure, but that it is a remarkably empty one at a distance where galaxy surveys can still map large patterns with useful clarity. In that sense, its position is scientifically fortunate. It is distant enough to belong unmistakably to the grand scale of cosmic structure. yet near enough that astronomers can examine the surrounding galaxy distribution and recognize a major underdense region. The direction toward Boötes also reminds astronomy of an important habit of language. Names on the sky often preserve the history of naked-eye stargazing even when the objects now studied are far beyond naked-eye sight. Ancient observers name star patterns by shape, season, or myth. Modern astronomers then attach those sky regions to galaxies, clusters, radio sources, quasars, and voids discovered by instruments. The result is a layered language in which the old visible sky and the deep invisible universe meet. The Boötes Void is one example of this meeting. It carries a classical sky name, but the thing itself is known only through the modern practice of measuring distances to galaxies and building a map far deeper than vision alone can reach, from Earth. Then, the Boötes Void is best imagined as a direction into depth. The foreground contains nearby stars of the Milky Way, including the bright markers that define the constellation. Far beyond them lie many galaxies, groups, and larger structures. Still farther along the same sightline, astronomers identify a broad region where galaxies become unusually sparse. This layered arrangement is crucial. The void is not a cavity beginning just beyond the visible stars. It is a remote underfilled region embedded in the distant cosmic web, reached only after the line of sight passes through vast amounts of ordinary intergalactic space and many other structures. Its naming can therefore be calm and precise. Boötes tells where to look on the sky. Void tells what kind of region astronomers find there. Together, the phrase does not describe a visible black patch or a nearby absence. It describes a faraway, underdense domain located in the direction of Boötes and recognized only when the sky is translated into a three-dimensional map of galaxies and distances. In this section of the journey, that is enough. The place has a direction, a depth, and a name that bridges ancient sky patterns and modern cosmology. It rests not among the bright stars that outline the constellation, but far behind them, in a remote volume of space where the great structure of the universe becomes clearer than the familiar shapes of the night sky. Around any great void, the first reality is not emptiness but structure. The Boötes Void is defined by what surrounds it as much as by what lies within it. Its outer rim is not a hard shell or a smooth surface. It is a broad and uneven region where galaxies, groups of galaxies, and larger chains of matter become far more common than they are in the sparse interior. This surrounding structure gives the void its shape in the same way that coastlines give shape to a sea. The sea has no wall around it, yet its extent becomes clear because land gathers at its edges. So it is here. The Boötes Void takes form because richer regions gather around a wide underdense volume and mark where the contrast begins. These richer regions belong to the cosmic web. Filaments are long strands where matter is more concentrated. Walls are broader features, sometimes called sheets, where galaxies spread across wide connected zones. Clusters sit at the denser knots, places where many galaxies collect under stronger gravity. The edge of a void is usually made from these elements together rather than from one simple boundary line. The Boötes Void follows this rule. Its rim is not drawn with geometric neatness. It appears as a changing border where the density of galaxies rises from unusual thinness toward the more typical richness of large-scale structure. In some directions the transition may seem sharper. In others it may spread more gradually across great distances. This matters because the word edge can mislead. In ordinary life, an edge suggests a definite limit, as with stone, wood, or metal. In cosmology, an edge is statistical. It is the place where the number of galaxies per unit volume becomes distinctly higher than it is inside the void. The change can be strong without being sudden. The Boötes Void has no physical wall of gas or dust. No barrier blocks passage from one side to the other. The boundary exists in the pattern of matter distribution. It is seen when maps show one large region with very few galaxies and a surrounding region where galaxies and groups become much more numerous. At these outer margins, the universe appears active in a quiet gravitational way. Matter is not standing still. Galaxies move through expanding space while also responding to local and regional gravity. Over immense timescales, matter tends to drift away from the sparsest regions and toward denser ones. Because of this, the boundaries of voids become clearer with time. The surrounding filaments and walls gather material that once had a more even spread. They do not build a perfect enclosure, but they do deepen the contrast. The Boötes Void therefore does not sit as a fixed hollow cut into a frozen cosmos. It exists within a slow flow of matter that strengthens the distinction between sparse interior and richer edge. The galaxies along these surrounding regions are not unusual merely because they happen to stand near a void. Many belong to the ordinary populations that make up the large-scale universe spiral galaxies with turning disks, elliptical galaxies with smoother shapes, smaller companion systems, and larger galaxy groups. What makes them important here is their arrangement. They appear in connected patterns that curve, stretch, and widen around the underdense volume. Their light marks out where matter has collected more successfully. In this way, the rim of the Boötes Void becomes visible not through direct sight of a border, but through the presence of many galaxies outlining a relative absence beyond them. The scale of these surrounding structures is immense. A filament in the cosmic web can extend across distances beyond any ordinary analogy. A wall can span regions so large that human geography becomes meaningless beside it. At the margin of the Boötes Void, these structures do not behave like local scenery. They belong to the grand architecture of the observable universe. A single galaxy is already vast. A cluster is larger still. Yet the rim of a giant void deals with arrangements of many such systems over volumes measured in hundreds of millions of light-years. This is why the edge feels both real and elusive. It is real in the data, in the rising density of matter. It is elusive because it stretches across dimensions too large for direct intuitive grasp. The surrounding structure also prevents a common misunderstanding. The Boötes Void is not a lonely circular gap surrounded by nothing else for great distances. It sits in a connected cosmos. Its rim joins other filaments, walls, and galaxy concentrations. Matter on one side of the void links onward to broader networks. The edge is therefore part of a continuing pattern rather than an isolated ring. This connectedness is essential. The void is one low-density region inside a much larger web, and its border is a local expression of that wider order. What seems at first like a single astonishing emptiness is, on larger inspection, one component of a universe built from contrast between concentration and scarcity. Because the rim is uneven, the very shape of the Boötes Void cannot be treated as perfectly simple. It is often described in broad terms, but no immense cosmic region comes with the precision of a machine-made object. The surrounding walls and filaments bulge in some places and narrow in others. Their arrangement influences how astronomers estimate the extent of the underdense space they contain. In this sense, the boundary is partly a matter of careful definition. Yet this does not weaken the physical reality of the void. It only reflects the truth that natural structures on the larger scales are irregular. coastlines, cloud banks, and mountain fronts all resist exact simplicity. So do the rims of cosmic voids. What the outer rim shows most clearly is that emptiness in cosmology is relational. A void is empty compared with its surroundings. Without denser surroundings, there would be no meaningful way to call a region underdense. The filaments and walls around the Boötes Void therefore do more than frame it visually. They give the concept itself its force. They establish the average against which the interior falls short. They reveal that the sparse volume is not merely distant or dark, but genuinely deficient in galaxies compared with the richer domains around it. The boundary is where that deficiency begins to stand out unmistakably. In this outer region, the Boötes Void remains a defined absence bordered by abundance. The eye of science first meets not the centre, not the few galaxies within, and not the detailed explanation of how it forms, but the broad ring of structure that announces its presence. The surrounding walls and filaments hold matter in long connected stretches, while the immense low-density volume opens between them. The border is soft, uneven, and statistical, yet it is strong enough to mark one of the most remarkable underfilled regions known in the large-scale universe. Once the outer rim is established, the Boötes Void can be considered in terms of sheer scale. Here the mind meets one of the main reasons this region remains so memorable in astronomy. It is not merely sparse, it is vast. The emptiness extends across a volume so large that ordinary astronomical landmarks begin to feel small inside it. A single galaxy, which already contains billions of stars, becomes only a minor point. A galaxy group becomes a scattered detail. Even larger structures lose some of their familiar weight when set against the estimated breadth of the void. This is the scale at which underdensity becomes difficult to absorb, not because the concept is obscure, but because the dimensions reach so far beyond ordinary spatial intuition. The Boötes Void is commonly described as measuring roughly 330 million light-years across. This figure is often used as a broad estimate rather than a perfectly fixed diameter, because the region is not a neat sphere with a sharp edge. Still, the number conveys the central truth. The void is enormous even by the standards of large-scale cosmic structure. Light itself, moving at the greatest known speed, requires hundreds of millions of years to cross such a distance. That fact gives a calm but severe measure of the region. The emptiness is not a local interval between neighbouring galaxies. It is a major domain in the architecture of the observable universe. To think about this size, it helps to compare not by forcing the void into familiar earthly images, but by placing it among astronomical scales. The Milky Way spans roughly 100,000 light-years. That is already an immense structure, so large that light takes about 100,000 years to cross it from one side to the other. The Boötes Void is much larger still. A great many galaxies the size of the Milky Way could be set one after another across such a span. This comparison does not turn the void into a collection of empty galaxy slots, yet it helps show the disproportion involved. The region is wide enough that the absence of galaxies across much of it becomes significant in a way that smaller gaps do not. Its shape, however, is not simple. The Boötes Void is often described in broad language as if it were an immense bubble or hollow sphere, and that picture is useful only at a first approximation. In reality, the structure is irregular. Its boundaries depend on how the surrounding galaxy distribution is measured, and how astronomers define where the underdense region begins and ends. Natural structures on cosmic scales do not form with polished symmetry. They stretch, bulge, taper, and blend into nearby features. The Boötes Void follows this general rule. It is approximately rounded in the loose sense that its sparse interior occupies a broad central region. Yet its actual form is less smooth, less balanced, and more dependent on the uneven arrangement of the surrounding cosmic web. This is why scale and shape cannot be separated. The reported width gives a strong impression of immensity, but that immensity belongs to a real three-dimensional pattern rather than an abstract geometric figure. The void occupies a great volume of space in which the density of galaxies falls far below what would normally be expected. That volume may be mapped somewhat differently from one study to another, because astronomy works with data points, survey limits, and statistical definitions. Even so, the overall conclusion remains stable. The Boötes Void is a genuinely giant underdense region. Its exact outline may shift with method, but its extraordinary size does not disappear under closer measurement. A void of this scale also changes how emptiness is understood. A small sparse region might arise by chance from limited local variation. Over larger and larger distances, chance alone becomes a less satisfying way to think about what is seen. The Boötes Void is large enough that it stands out as a major feature in the cosmic matter distribution. It is part of the larger pattern by which matter and galaxies collect into walls and filaments, while broader regions become depleted. The important point here is not the detailed mechanism, but the scale of the result. The underdense domain grows so large that it takes on the status of a structural component of the cosmic web rather than a minor fluctuation within it. The language used about the void sometimes includes the phrase "one of the largest known." That phrasing carries caution. Astronomy continues to improve its surveys, and definitions of voids can vary. Some voids may be measured differently, split into smaller parts, or combined into larger underdense complexes depending on method. For that reason, a strict ranking can be less important than the broader classification. The Boötes Void belongs among the most remarkable giant voids identified in galaxy maps. Its fame comes not from a fragile record that depends on one decimal value, but from the persistent impression that it occupies an exceptionally large and sparse volume compared with the average texture of the nearby large-scale universe. Its largeness is felt not only in width but also in volume. When a region expands in linear size, the total space it contains grows much more rapidly. A broad underdense sphere, even an approximate one, encloses an immense amount of cosmic real estate. In such a volume, astronomers would normally expect to find many more galaxies than are actually observed. This contrast between expected richness and observed sparseness deepens the significance of the void. The emptiness is not judged by darkness alone, and not by a single missing object. It is judged by the scale of the region and the relative lack of the galaxies that would ordinarily help fill such a space. At this magnitude, the Boötes Void also acquires a certain visual power in maps of the universe. Galaxy surveys often present distant structures as points and patterns in 3 dimensions. In those maps, dense regions appear textured and crowded. The void appears as a broad interruption in that texture. It is not a perfect black globe drawn in ink. It is more subtle than that. Yet the gap is large enough that it seems almost to open physically within the mapped structure. This visual effect contributes to its reputation, but the reputation remains rooted in measurement. The region commands attention because its dimensions make the underdensity unmistakable. The scale of the hollow therefore becomes the central fact of this region. The Boötes Void is not only empty by comparison with its surroundings, it is empty across a span so great that the comparison itself becomes arresting. It occupies a huge volume, reaches across hundreds of millions of light-years and resists neat geometric description while still remaining plainly enormous. In calm scientific terms, that is enough to understand why it holds such a firm place in cosmology. The size alone makes it a striking member of the universe's largest known underdense regions. The Boötes Void enters astronomy not as a visible abyss on the night sky, but as an absence uncovered by measurement. Its discovery belongs to a period when astronomers are learning to turn the apparent spread of galaxies across the sky into a true three-dimensional map. A flat star chart can show direction, but direction alone cannot reveal whether galaxies that seem close together are in fact neighbours or merely happen to lie along the same line of sight. To understand the large-scale structure of the universe, distance must be added. The key tool for that work is redshift, the stretching of light toward longer wavelengths as galaxies recede in the expanding universe. Redshift does not act like a label attached to a galaxy by nature for easy reading. It must be measured from the light the galaxy sends. When that light is spread into a spectrum, dark and bright features appear at known wavelengths. If those features are shifted toward the red end compared with where they would be seen in laboratory conditions, astronomers can determine how strongly the light has been stretched. In the broadest sense, a larger redshift usually means a greater cosmic distance. This relation is not used carelessly, and it is not exact in every small detail, but across large scales it becomes one of the central methods for mapping the deep universe. Before such surveys grow wide and systematic, a vast empty region like the Boötes Void can remain hidden in plain sight. On a two-dimensional sky, scattered galaxies in the direction of Boötes do not by themselves announce that an enormous underdense region lies at a certain depth. The foreground and background mingle visually. Nearby galaxies and faraway galaxies can appear in the same patch of sky. Only when many galaxy distances are measured does the hidden structure emerge. The discovery therefore depends on patience, on instrument work, and on the growing ability to collect redshifts for many galaxies across one region, rather than for only a few isolated objects. In the early 1980s, this effort reveals something striking. Astronomers studying galaxies in the direction of Boötes gather redshift measurements and begin to see that a very large range of space contains far fewer galaxies than expected. The absence is not a small local gap. It extends across a substantial part of the mapped region. Instead of a roughly even spread, the data suggest a broad hollow in the galaxy distribution. This is the moment in which the Boötes Void begins to take scientific form. It is born not from one dramatic image, but from many measured points, and from the unusual silence between them. The process is quiet and exacting. Each galaxy contributes one position on the sky and one estimate of distance from its redshift. Taken alone, a single point says little about the larger structure. Taken together, many points begin to reveal patterns. Dense regions appear where galaxies cluster in the map. Strands and sheets begin to show themselves where points align over great spans. A void becomes visible when those points fail to appear across a wide volume where a richer distribution would normally be expected. In this sense, the Boötes Void is discovered through subtraction. The discovery lies in the scarcity of markers, made meaningful only because enough measurements exist around it. This kind of finding requires trust in method as much as surprise at result. A large gap in the data can, in principle, come from incomplete observation, weak instruments, or a survey that misses faint galaxies. For that reason, astronomers do not treat absence lightly. They examine whether the apparent hollow reflects the actual distribution of galaxies or only the limits of the observing program. In the discovery stage, the striking feature is that the gap is large enough and coherent enough to demand attention. It does not look like a few missed objects. It looks like a broad underfilled region in the three-dimensional map itself. The name Boötes Void gradually attaches to this mapped emptiness because the region lies in the direction of the constellation Boötes and because the structure revealed there is best described as a void in the galaxy distribution. The term is direct, almost plain. It says what is observed without forcing a more dramatic interpretation. There is no implication that space has been torn open or cleared by some violent agent. The redshift survey reveals a region where galaxies are strikingly sparse. That alone is enough to justify the name and enough to give the discovery lasting force in cosmology. At the level of practice, the discovery also marks an important transition in how the universe is understood. Earlier astronomy often studies galaxies as individual systems, comparing their shapes, brightness, or internal contents. Redshift surveys shift attention toward relationships among many galaxies across vast distances. They make it possible to study the texture of the universe itself. The Boötes Void stands as one of the memorable results of that transition. It shows that the large-scale universe is not simply populated by galaxies of many kinds, but arranged in broad patterns that include enormous deficits as well as rich concentrations. There is also a human restraint built into this stage of the story. The first recognition of the void does not come with complete certainty about every boundary or every implication. Discovery, in astronomy as in other sciences, often begins when a pattern becomes too strong to ignore even though its full meaning remains under study. That is what makes redshift surveys so powerful. They allow structure to emerge before it is fully explained. The Boötes Void first appears in this measured but incomplete light, as a mapped region whose sparseness is too great to pass as ordinary variation. So the discovery through redshift is both technical and quiet. Telescopes gather light from distant galaxies. Spectra reveal shifted features. Shift becomes distance, and distance turns a patch of sky into depth. When enough depths are assembled, the ordinary appearance of a constellation direction gives way to a remarkable fact about cosmic structure. A huge underdense region stands out where many galaxies might have been expected. The Boötes Void enters knowledge at that point, not as a visual spectacle, but as a pattern in measured recession and distance. A silence in the galaxy map made visible only by the patient geometry of redshift. After the first redshift maps reveal an unusually broad gap in the direction of Boötes, the next scientific task is not interpretation, but verification. Astronomy treats a surprising absence with caution. A rich cluster can often announce itself with many bright galaxies close together, but a void depends on missing objects, and missing objects are always more difficult to trust. An empty region can appear in a map for more than one reason. The sky coverage may be incomplete. Some galaxies may be too faint for the instruments used. Dust, brightness limits, or sampling choices may distort the picture. The early recognition of the Boötes Void therefore leads naturally to a second stage, in which astronomers ask whether the hollow in the data is a real feature of the universe or only a product of the way the survey is made. This is where follow-up work becomes essential. The region is observed again with additional measurements, broader sampling, and closer attention to possible bias. In astronomy, a bias of this kind is often called a selection effect, meaning that the method of observation may favor some objects and miss others. If a survey mainly detects brighter galaxies, then a region filled with faint galaxies might appear emptier than it truly is. If the sky coverage is patchy, an under-observed area might resemble a genuine gap. To confirm a cosmic void, astronomers must show that the scarcity remains even when these possibilities are considered carefully. The Boötes region proves strong enough to survive that scrutiny. Further redshift work continues to find a major underdense volume rather than a hidden crowd of overlooked galaxies. The gap does not vanish when more data points are added. It does not collapse into an ordinary fluctuation once the survey becomes more systematic. Instead, the broad impression remains the same. Galaxies are present around the region in much greater numbers than within it. The contrast is large, coherent, and extended across a volume too great to be explained by a minor observational accident. The void becomes more secure not because one perfect measurement settles the matter, but because repeated examination continues to support the same underlying pattern. This process of confirmation unfolds in a measured way. Astronomers compare the region with neighboring parts of the sky and with what large-scale structure studies generally suggest about galaxy density at similar depths. They consider whether the instruments reach faint enough limits to detect galaxies that should be visible if the space were more typical. They inspect whether the apparent hollow changes drastically when different samples are used. A false void would tend to weaken under these tests. A real void would continue to show a serious deficit of galaxies even as the map grows denser and more reliable. In the case of the Boötes Void, the deficit remains. The very size of the region helps make the confirmation persuasive. A small gap can sometimes arise from sparse sampling. A giant one is harder to dismiss. The Boötes Void occupies such a wide domain that the probability of explaining it away through a few missed observations becomes less convincing. This does not mean astronomers become careless. It means the scale of the feature adds weight to the repeated result. When many added measurements still fail to populate a broad volume that would ordinarily contain far more galaxies, the absence itself becomes a stable scientific observation. The void is no longer merely a striking first impression in a survey. It becomes a recognized part of the mapped large-scale universe. Follow-up studies also help refine the character of the gap. The early discovery stage reveals that something unusually empty is present. The confirmation stage clarifies that the emptiness is not absolute, not perfectly bounded, and not based on a simple visual impression. Instead, the void is established as an underdense region, meaning a volume where the number of galaxies lies far below the cosmic average for comparable regions. This language matters. It protects the science from the exaggeration that often gathers around large empty places. The Boötes Void is not proved real because astronomers find nothing there at all. It is proved real because they continue to find far less there than expected. Another important part of confirmation is the growth of confidence across the astronomical community. A discovery seen in one paper becomes more secure when later work, using other observations and related methods, reaches a compatible conclusion. The Boötes Void gains this kind of acceptance gradually. It moves from a surprising result toward a reference point in discussions of cosmic structure. That transition depends less on drama than on repetition. Science usually becomes confident through persistence. The feature holds under re-examination, and so it becomes part of the working map of the universe rather than a temporary curiosity. This stage also reveals something about the discipline of cosmology itself. The universe is too large to inspect all at once, and every survey begins with limits. Telescopes do not sample every galaxy equally. Spectra take time to gather. Distances require careful interpretation. For these reasons, Large-scale structures are not discovered in a single act of seeing. They are assembled from measurements and then tested against the weaknesses of those measurements. The confirmation of the Boötes Void is a clear example of that discipline. Astronomers do not simply accept emptiness because it seems impressive. They challenge it, retest it, and only then allow it to stand. By this point, the region in Boötes is no longer best described as a possible gap that may disappear with better data. It is better described as a confirmed giant void, even though its exact shape and detailed population remain matters for further study. That balance is important. Confirmation does not mean every uncertainty is removed. It means the central claim survives. A major underdense region exists there. Additional work may sharpen its boundaries, improve galaxy counts, or refine statistical definitions, but the basic reality no longer depends on one fragile observation. The gap has endured enough scrutiny to become a real feature in the mapped distribution of galaxies. So the confirmation of the gap is a quiet strengthening of reality. The first surveys reveal an astonishing lack. The later surveys ask whether the lack is only apparent. The answer, steadily and cautiously, is that the underdensity remains. The Boötes Void persists through wider observation, through concern about faint-missed galaxies, through checks against survey bias, and through the ordinary skepticism of science. What first appears as an absence in data becomes, by repetition and restraint, a solid astronomical fact, a vast region where galaxies are truly and strikingly sparse. The word empty carries a strong meaning in ordinary language. It suggests a container with nothing inside, a room without furniture, a vessel without water, a field without objects. In cosmology, the word must be softened and made more precise. When astronomers describe the Boötes Void as empty, they do not mean that it contains nothing at all. They mean that it contains far less matter than a more typical region of the universe on the same scale. The emptiness is real, but it is relative. It is an emptiness of scarcity, rather than an emptiness of total absence. This distinction is essential because space itself is never merely a blank stage waiting to be filled. Even in regions far from galaxies, space still contains physical reality. Gravity remains present. Radiation passes through. Thin gas may drift between galaxies. Dark matter continues to shape the region even though it emits no light. The Boötes Void, therefore, is not a clean hole cut out of existence. It is a vast underdense domain in which the known ingredients of the universe are still present, but present in reduced amount when compared with richer parts of the cosmic web. The first and most visible part of this scarcity concerns galaxies. In dense regions of the universe, galaxies can be found in large numbers, grouped into clusters, stretched along filaments, or spread through broad walls. In the Boötes Void, galaxies are much rarer. The difference is not small. It is strong enough that the region stands out as a major gap in galaxy maps. Yet even here, the phrase much rarer does not mean none. A few galaxies do exist within the void. Their presence matters because it reminds astronomy that a cosmic void is not an absolute clearing. It is a region where the expected richness fails to appear, not a region where every galaxy has been excluded. The same principle applies to gas. Between galaxies there lies intergalactic gas, usually very thin, often heated or ionized, meaning that atoms have lost one or more electrons. This gas does not behave like the thick air near Earth, or like a visible cloud in the sky. It is exceedingly sparse. In a void, it becomes sparser still. Even so, it does not vanish completely. The Boötes Void contains intergalactic material at low density, spread across huge distances. That gas may be difficult to detect directly, and much of it may remain extremely faint. But its likely presence follows from the simple fact that the void belongs to the ordinary universe rather than existing outside it. Dark matter is even more important in this regard. Although it cannot be seen directly with telescopes in the way stars and glowing gas can be seen, it is understood to make up a large portion of the matter content of the universe. The Boötes Void is underdense in dark matter as well as in ordinary matter. Yet underdense does not mean absent. The invisible gravitational framework persists there in thinner form. This matters because galaxies do not form independently of dark matter. Where dark matter is reduced, galaxy formation is generally less effective. The sparse galaxy population of the void reflects not only a lack of visible matter, but a more general thinness in the total matter distribution. Radiation also continues to cross the region. Light from distant galaxies passes through. Background radiation fills space on the larger scales. The void does not interrupt the presence of electromagnetic radiation as if it were a sealed chamber. It remains part of the same transparent cosmic volume through which photons travel over immense distances. In that sense, the void is dark mainly because it contains few luminous objects within it, not because light itself cannot enter or leave. Darkness in cosmology often means lack of local sources rather than blockage. It is also useful to separate emptiness from silence in a literal sense. Space does not carry sound in the ordinary way because sound requires a material medium such as air or water. A void is therefore not silent because it is especially empty. It is silent in the same basic way that all near-vacuum regions of space are silent. What changes in the Boötes Void is not the presence or absence of sound, but the density of matter. The scientific meaning stays with counting, mapping, and comparing. The region contains less material than average. That is the whole force of the term. Because human language tends to push emptiness toward extremes, the Boötes Void is often misunderstood as a place where almost nothing exists in any sense whatsoever. This is too strong. The region is not a tear in the fabric of space. It is not a place where the laws of physics fail to apply. It is not a chamber beyond the reach of matter and energy. The same fundamental laws that govern denser regions also govern this one. Gravity acts there. Light crosses there. Matter persists there in low concentration. The void is exceptional in degree, not in kind. That degree, however, remains profound. When astronomers say that a region is underdense, they are making a comparison against the average large-scale distribution of matter. A void can therefore be physically rich in sheer size while still being poor in content. The Boötes Void occupies an immense volume. Across such a volume, even a reduced density may still amount to a substantial total quantity of matter when considered all at once. Yet what defines the region scientifically is not the total sum spread across its full breadth. What defines it is the fact that the matter is spread so thinly that galaxies become scarce and the usual texture of the cosmic web fades dramatically. In this way, emptiness in the Boötes Void becomes a measured condition rather than a poetic impression. It refers to low density, sparse galaxy counts, thin intergalactic material, and a reduced dark matter framework. It does not refer to nothingness. The void remains part of the universe in every physical sense. It contains space, gravity, matter, radiation, and time. What it lacks is abundance. Its emptiness is a shortage written across an enormous scale, not a cancellation of existence. So when the Boötes Void is called one of the emptiest places in the universe, the phrase carries both truth and restraint. It is true because the region shows an extraordinary lack of galaxies and a greatly reduced matter density compared with its surroundings. It is restrained because the emptiness is never perfect. A few galaxies remain, thin gas remains, dark matter remains in lower concentration, radiation continues to pass through. The void is real, but it is not absolute. It is the cosmic meaning of almost empty, defined with care across one of the largest sparse regions known. To understand how a region like the Boötes Void begins, attention turns away from the present map of galaxies and back toward the early universe, when no galaxies yet exist and no void stands open in anything like its current form. At that early stage, matter is spread with remarkable smoothness across space. Yet the smoothness is not perfect. Very small differences in density are already present. Some regions contain slightly more matter and energy than average. Others contain slightly less. These differences are tiny, but they are real, and they provide the starting pattern from which the later large-scale structure of the universe gradually emerges. The early universe is hot, dense, and filled with radiation and matter interacting closely. In that state, the contrast between denser and thinner regions is extremely small. Nothing in this young cosmos resembles the great emptiness of the Boötes Void as it is known much later. There are no giant hollows, no rich walls of galaxies, and no long filaments stretching between clusters. There is only a nearly uniform cosmic medium marked by faint irregularities. These irregularities are not flaws in the universe. They are part of its basic physical history. Without them, matter would remain too evenly spread for stars, galaxies, clusters, or voids ever to develop in the forms now observed. Astronomers infer the presence of these early variations from several lines of evidence, especially from the relic radiation that fills the universe, often called the cosmic microwave background. This background light preserves a picture of the young universe when matter and radiation become free to travel more independently through space. In that ancient light, tiny temperature differences appear across the sky. These differences correspond to slight variations in density in the early cosmic material. The pattern is delicate, but its importance is profound. It shows that the beginning of a large-scale structure lies in minuscule departures from perfect uniformity. A denser region in that early medium contains a little more gravitational pull than its surroundings. A thinner region contains a little less. At first, the contrast is so slight that the difference seems almost negligible. Yet gravity is patient. Over immense stretches of cosmic time, it can amplify very small initial conditions into very large outcomes. The origin of a void therefore does not require a dramatic event that clears matter away. It begins with a region that is already slightly underdense compared with neighbouring space. The deficit is tiny at first, but it gives that region a distinct future under the slow action of gravity in an expanding universe. This early underdensity is the true ancestor of a cosmic void. It is not empty in any strong sense. It is simply a place where matter is a little less concentrated than average. That small shortage means the region has slightly less gravity pulling inward from within itself. Nearby denser regions, by contrast, have slightly stronger inward pull. Over time, matter tends to collect more effectively where the density starts higher, while the slightly thinner region becomes relatively poorer. The crucial point at this stage is that the difference begins as a matter of degree so small that it can only be described statistically. The later vastness of a void is already hidden inside a barely perceptible imbalance. The source of those first imbalances reaches back to the earliest known physical conditions of the universe. Modern cosmology describes a very early phase in which the young universe undergoes rapid expansion and carries forward tiny fluctuations that later serve as seeds for structure. The exact deepest origin of those fluctuations remains part of fundamental cosmological theory. But observations strongly indicate that the early universe is not perfectly smooth. It carries slight variations from place to place, and those variations have the right general character to grow into the web-like arrangement of matter seen much later. In that broad sense, the origin of the Boötes Void lies not in a local accident near the present age of the cosmos, but in the first faint unevenness written into the young universe. At this early stage, the future void cannot be separated from the future-rich structures around it. The same initial field of tiny fluctuations contains both the seeds of denser regions and the seeds of thinner ones. One cannot exist meaningfully without the other. A place that starts a little above average and a place that starts a little below average are born together as part of one shared pattern, the later cosmic web. With its crowded filaments and broad hollows, is therefore already implicit in the subtle texture of the early universe. The Boötes Void begins as one part of that texture, a faint region of lesser density that is destined, through the ordinary laws of cosmic evolution, to become more distinct over time. There is no need at this stage to imagine violence, explosion, or removal. The underdense region is not carved out. No force scoops matter from the inside as if hollowing a cavity in wood or stone. The beginning is gentler than that. Matter is simply not distributed with perfect equality. The future void starts with slightly less to begin with. This quieter symmetry is enough. In cosmology, very small differences matter because they act across immense distances and enormous durations. The grandest structures need not begin grandly. They may arise from the continued consequence of a difference so slight that only precise measurement reveals it in the young universe. This way of thinking also explains why voids are natural within standard cosmology. They do not stand outside the expected behavior of an evolving universe. A nearly uniform beginning, marked by tiny fluctuations, naturally produces both concentrations and deficits as gravity acts over time. The Boötes Void is striking because of its scale, but its first cause belongs to the same general process that eventually leads to galaxies, clusters, and the larger web itself. Its origin is not a separate mystery detached from ordinary structure formation. It is one expression of the same initial unevenness that shapes the rest of the cosmos. So the early region that will one day become the Boötes Void begins as a slight underdensity in the young universe, preserved within a broad field of tiny fluctuations. The contrast is almost imperceptible at first. Matter remains nearly uniform. Radiation fills space, and no visible sign yet marks the immense emptiness to come. But the initial condition is present. A little less matter lies there than elsewhere. A little less gravity gathers there from within. Across cosmic time, that small beginning becomes consequential. In this earliest region of the story, the Boötes Void exists only as a faint imbalance in the young universe, a subtle shortage from which one of the most remarkable sparse domains in the cosmos eventually arises. Once a slight underdensity is present in the early universe, its later growth follows a quiet but persistent logic. The region does not remain fixed at its original weakness. As cosmic expansion continues and gravity pulls matter toward denser surroundings, the underdense area gradually loses material relative to its neighbours. This is the basic way a void grows. It becomes not an empty chamber that expands by force from within, but a region whose matter content falls behind more and more as surrounding structures gather strength. The Boötes Void belongs to this long process of widening contrast, where a small early shortage turns into a broad, mature sparseness. The expansion of a void is not the same as the overall expansion of the universe, though the two happen together. The universe expands everywhere on large scales. A void, however, tends to expand in a relative sense faster than denser regions around it because matter is flowing away from its interior towards surrounding walls and filaments. This center holds less gravity of its own, so it cannot retain matter as effectively. Nearby denser regions exert stronger influence, and over immense spans of time the underdense volume becomes more evacuated. In this way, the void grows not by adding emptiness as a substance, but by losing comparative share in the cosmic distribution of matter. This gradual outward drift of matter changes the shape of the surrounding web. Material that leaves the sparse region does not vanish. It contributes to the growth of denser structures nearby. Filaments become richer, walls become more defined. Clusters at the knots of the web gather additional mass over time. The void and its rim therefore evolve together. As the interior becomes thinner, the surrounding structures become more pronounced. This mutual sharpening is one of the central reasons the large-scale universe develops such visible contrast between crowded and sparse regions. A void is not only a place with little matter, it is also a participant in the transfer of matter toward the structures around it. At first, many underdense regions are modest. The young universe does not begin with immense hollows already in place. It begins with a field of many fluctuations at different scales and strengths. Some underdense regions remain relatively small, others grow larger as surrounding matter drains away. Over time, neighbouring underdense zones can begin to interact. If two sparse regions lie close enough together, the denser boundary between them may weaken as matter continues to move outward toward richer structures farther away. The contrast that once separated the two regions can fade. When that happens, the smaller voids effectively merge into a larger one. This merging process helps explain how very large voids can arise without requiring a single enormous underdensity at the beginning. A giant void may be the mature outcome of several smaller sparse domains that expand, press against one another, and gradually lose the dividing ridges between them. The language of merging should be understood carefully. The voids do not collide like solid bodies. They do not strike or break. Rather, the matter between them becomes less able to stand as a meaningful separator. The underdense character of each region spreads until they are better described as one larger sparse volume than as two distinct smaller ones. The result is a kind of coalescence shaped by gravity and cosmic expansion. This gives void evolution a layered quality. A void grows from within by becoming relatively thinner, and it also grows outward by joining with neighbouring underdense regions when the intervening matter drains away. The Boötes Void is understood within this general picture. Its vast scale does not require an extraordinary mechanism separate from the usual evolution of large-scale structure. Standard cosmology already allows for smaller voids to widen, and for neighbouring sparse regions to combine into broader cavities over long spans of cosmic time. The remarkable size of the Boötes Void makes it memorable, but the underlying behaviour belongs to the expected development of the cosmic web. The process remains statistical rather than perfectly geometric. Not all parts of a void boundary expand at the same rate. Not all neighbouring underdense regions merge cleanly. The surrounding filaments and walls vary in strength and shape. Some barriers between sparse zones may persist for a long time if enough matter remains concentrated there. Others may fade more readily. This gives mature voids an irregular form. They are not polished bubbles. They are natural products of uneven matter flow across immense distances. Their growth depends on local context within the wider web, and that context is never perfectly symmetrical. In this ongoing development, the interior of a void becomes dynamically simple in one sense and structurally significant in another. It becomes simple because little remains there to resist the general outward drift of matter. The low density leaves the region with weaker internal gravitational competition, yet it remains significant because the very lack of matter influences the paths along which surrounding material moves. The underdense zone helps shape the broad arrangement of the web by directing matter away from itself and toward its margins. In that sense, a void is not passive emptiness. It is an active part of the large-scale gravitational landscape, defined by deficiency but still shaping the pattern around it. There is also a timescale to this story that demands patience. Void growth does not happen suddenly. It unfolds over billions of years. A region that begins only slightly underdense must persist through enormous stretches of expansion before it becomes one of the grand, sparse domains that stand out in galaxy surveys. This long duration is important because it shows how modest beginnings can have major outcomes when the governing process is steady and the available time is immense. The Boötes Void does not need a catastrophic origin to become extraordinary. It needs only the quiet persistence of gravity acting on an initial imbalance across the full age of cosmic structure formation. As the void expands and merges, its interior becomes increasingly unlikely to host the dense conditions needed for frequent galaxy formation. Meanwhile, the boundaries, enriched by outward matter flow, continue to mark where structure is strongest. The distinction between inside and outside therefore deepens with age. What was once a slight dip in density becomes a mature underdense basin in the cosmic landscape. Its size reflects not only its beginning, but also the history of how surrounding matter responds and how neighbouring sparse zones evolve alongside it. So the growth of the Boötes Void can be understood as the compounded result of relative expansion and gradual merging. Matter slips outward toward denser structures. Smaller sparse regions widen. Dividing ridges thin and sometimes dissolve. The underdense domain becomes broader, emptier, and more coherent as part of the surrounding web. Nothing violent is required. No special clearing force is needed. Across immense time, a little less matter becomes much less matter, and several quiet deficits can combine into one of the largest sparse regions known in the observable universe. At the boundary of a great void, gravity does not appear as a visible force pulling on matter with any dramatic sign. It works through patient imbalance. The Boötes Void contains less matter in its interior than the regions around it, and this difference creates the gravitational character of its edge. A denser region exerts a stronger pull than a thinner one. Because of that, matter near the boundary tends to feel a greater attraction toward the richer filaments, walls, and groups of galaxies that surround the void than toward the sparse interior behind it. This is the quiet principle that shapes the margin. The edge grows clearer because gravity is stronger where matter is already more abundant. In this setting, the boundary is not a fixed line drawn across space. It is a broad transition zone in which gravitational influence changes gradually with the distribution of matter. Near the sparse interior, the pull from all directions is relatively weak because the matter density is low. Closer to the surrounding structures, the pull becomes less even. Filaments and walls contain more mass, so they begin to dominate the local flow. A galaxy, a cloud of gas, or a concentration of dark matter near the edge is therefore not equally balanced between the inside and the outside. It is more likely to drift toward the denser side over immense spans of time. In this way, the edge is shaped not by a barrier, but by a difference in gravitational preference. This process can be described simply. If one side of a region contains more matter, then that side has more gravity. Matter nearby tends to move in that direction unless some other influence counters it. In the large-scale universe, no ordinary force holds material in place against this trend across billions of years. The result is a slow outward migration from the underdense zone toward the richer structures at the margin. The Boötes Void therefore becomes emptier because the edge keeps winning this quiet contest. The surrounding web draws matter away more effectively than the interior can retain it. The same principle applies to both ordinary matter and dark matter. Ordinary matter includes gas that can later take part in galaxy formation. Dark matter forms much of the deeper gravitational framework. Near the boundary of a void, both respond to the uneven pull created by the surrounding density field, which is the large-scale pattern of where matter is thick and where it is thin. Because the Boötes Void is underdense in the total matter distribution, not merely in visible galaxies, its edge represents a real gravitational gradient rather than a visual accident. The denser rim is not only brighter in maps, it is more massive, and that mass gives the boundary its slow authority. This helps explain why the contrast between void interior and void edge grows stronger over time. A slightly underdense region in the early universe already begins with less inward pull from within itself. As neighbouring regions gather matter, their gravitational strength increases. The more the edge grows in mass, the more effectively it draws additional material outward. The process reinforces itself. The sparse region loses matter, which makes it still less able to resist further drainage. The denser boundary gains matter, which strengthens its influence still more. This does not lead to a sudden collapse or a runaway event visible on human timescales. It simply means the large-scale pattern sharpens steadily as the universe ages. At the margin of the Boötes Void, gravity also helps determine the motions of galaxies already near the edge. These motions are small compared with the full expansion of the universe, but they matter for structure. A galaxy does not merely ride the general expansion of space without regard to local surroundings. It also responds to nearby concentrations of mass. This local motion relative to the broader expansion is sometimes called peculiar motion, meaning motion that reflects the gravitational environment rather than the general recession caused by cosmic expansion. Near a void boundary, such motions tend to carry galaxies away from the underdense interior and toward the denser structures that define the rim. The boundary is therefore not only a contrast in location, it is also a pattern in motion. This outward preference has a subtle collective effect. Over time, matter streams away from the least populated region and accumulates along the surrounding structures. The edge becomes a zone where the web is reinforced. More mass means more gravitational attraction, and more attraction draws in more mass. Yet this must be understood in a measured way. The rim does not become an impenetrable shell. Matter still remains distributed through space without a hard surface. Galaxies can lie near the transition. Gas can stretch across broad volumes. The edge is strengthened by tendency, not sealed by force. Gravity shapes probability and long-term flow rather than building a wall. Because the Boötes Void is so large, these gravitational effects operate across extraordinary distances. No single galaxy at the edge feels the pull of the entire void in a simple direct sense. Instead, each part of the boundary reflects the surrounding pattern of filaments, groups, and walls nearby. The combined result across the whole region is an outward drainage from the sparse interior and a persistent rise in structure at the margin. This local nature of gravity helps explain why the rim is irregular. Some parts of the boundary border stronger concentrations of matter than others. In those places, the outward pull is more effective. Elsewhere, the transition may be gentler. The edge records the uneven geography of mass around the void. The boundary therefore becomes a place where the large-scale logic of the cosmic web is easiest to see. Inside the void, little matter remains to shape complex structure. Far outside it, the web continues into other concentrations and sparse regions. But at the rim, the contrast becomes direct. One side offers a broad underdense volume with weak internal pull. The other side offers the richer connected structures where gravity gathers matter more strongly. The edge is where these two conditions meet, and gravity decides the balance. Matter moves according to that balance, slowly but persistently, and the rim is maintained. In calm scientific terms, the boundary of the Boötes Void is a gravitational frontier made not of surfaces but of gradients. A gradient is simply a gradual change from one condition to another. Here the change is from lower matter density to higher matter density, and with that change comes a difference in gravitational influence. The sparse interior cannot compete equally with the denser surroundings. Matter near the transition therefore tends, over long times, to join the richer structures. That is why the void remains underdense, and why its edge remains meaningful. So gravity at the boundary is neither violent nor mysterious. It is the plain consequence of uneven mass distributed across an expanding universe. The Boötes Void has less matter within. The surrounding walls and filaments have more. Their stronger pull draws material outward, strengthens the edge, and preserves the contrast between scarcity and concentration. The rim is broad, irregular, and statistical, yet its governing principle is simple. Where matter is richer, gravity is stronger, and over cosmic time that difference shapes the frontier of one of the largest known voids. Even within one of the largest known underdense regions, the galaxy count does not fall to zero. A few galaxies remain inside the Boötes Void, scattered across its enormous volume like rare light separated by great dark intervals. Their presence is important because it corrects a common misunderstanding. A void is not defined by complete absence. It is defined by unusual scarcity. The galaxies that remain do not erase the void. They help show more clearly what the word means in cosmology. The region is not empty in the absolute sense. It is empty in the comparative sense, with far fewer galaxies than would normally be expected across such a vast space. These surviving galaxies do not gather into anything like the dense arrangements seen in richer regions of the cosmic web. They do not produce a strong wall, a cluster, or a busy filament crossing the interior. Instead, they appear sparsely, often separated by distances that reinforce the impression of an underfilled domain. In a more typical cosmic environment, a broad volume of this size would contain many more galaxies and many more links among them. Inside the Boötes Void, the pattern is thin. The few galaxies present serve less as a competing structure and more as isolated reminders that underdensity is not the same as nothingness. Their existence also shows that the formation of galaxies is difficult in a void, but not impossible. The matter density inside the region is reduced, not cancelled. Dark matter remains present at lower concentration, and ordinary gas still exists in thin form. Under some conditions, these ingredients can still collect enough to form galaxies, especially smaller systems that require less total material than massive clusters or giant concentrations. The result is a sparse population that arises within the broader shortage. Each galaxy inside the void represents a local success of structure formation in a region where the overall conditions are less favourable. This helps explain why the few galaxies found there do not contradict the nature of the void. Their presence is exactly what a careful scientific description would allow. If the interior contained many galaxies distributed with ordinary richness, then the region would no longer deserve the name void. But a small surviving population is fully consistent with the concept. The Boötes Void remains remarkable not because every trace of structure has been removed, but because the amount of structure left behind is so limited when measured against the region's enormous size. The rarity is the point. A handful of islands does not stop a sea from being a sea. The galaxies that remain are also not all identical. A void can contain different kinds of galaxies, including smaller and less crowded systems that manage to form in local pockets of matter concentration. Some may appear relatively modest in mass and brightness when compared with the larger, more evolved systems often found in denser cosmic settings. This does not make them unimportant. On the contrary, their existence provides evidence that the interior of a void is still part of the ordinary universe, governed by the same physics as anywhere else. Gravity still gathers matter when enough local concentration develops. Gas can still cool. Stars can still form. The process is simply less common and often less amplified than it is where matter is more abundant. In maps of the Boötes Void, these galaxies can seem almost incidental because the human eye is easily captured by the great underdense volume around them. Yet scientifically, they matter. They reveal that the void is a low-density terrain, not a clean cavity. They also make clear that the interior has structure at a weak level. Even a great void is not uniform in every part. Some places inside it are thinner than others. Some local concentrations become sufficient to host galaxies. The result is not a featureless emptiness, but a sparse and uneven interior in which a few structures persist. What makes those galaxies so striking is the contrast between their existence and their setting. A galaxy is already a large and complex system, containing stars, gas, dust, dark matter, and long histories of formation. To find such an object inside a giant void can seem surprising at first because the surrounding volume is so depleted. But the surprise fades when the logic of underdensity is kept in mind. A void lowers the probability of galaxy formation across a vast region. It does not reduce that probability to zero at every point. Local conditions still vary. Small pockets of relatively greater density can remain within the larger sparse field. Where those pockets are sufficient, galaxies can emerge. The vast size of the Boötes Void is what keeps these surviving galaxies from changing the overall picture. In a much smaller region, a few galaxies might fill a large fraction of the available space and make the place seem only mildly sparse. In a void measured across hundreds of millions of light years, the same number remains tiny by comparison. The scale is so overwhelming that even a visible population of galaxies can leave the region profoundly underfilled. This is one reason the Boötes Void keeps its reputation. The galaxies that remain are not numerous enough to compete with the enormity of the emptiness around them. Their presence may even make the void easier to understand. If the region were described as containing absolutely nothing, it would sound less like a natural outcome of cosmic evolution and more like an impossible exception. But a few surviving galaxies make the structure more physically plausible. They fit the expectation that reduced matter density leads to reduced, not forbidden, structure formation. The Boötes Void then appears not as a break in the laws of cosmology, but as an extreme example of them. Scarcity reaches a remarkable level, while a small residue of galaxies remains as part of the same continuous physical picture. These galaxies also help define the void statistically. Their positions and numbers contribute to the measurement of how underdense the region actually is. A void is described by the deficit of galaxies compared with the average, not by an absolute visual impression. Every galaxy inside the Boötes Void becomes part of that calculation. They do not weaken the concept by existing. They sharpen it by allowing astronomers to measure how strong the deficit really is. The region stands out precisely because the count remains so low despite the immense volume surveyed. So the galaxies that remain inside the Boötes Void are not a problem to be explained away. They are part of the true nature of the region. They show that a cosmic void is sparse, not non-existent. They reveal that local structure can still arise within a broad shortage of matter. They confirm that the Boötes Void belongs to the ordinary physical universe even while it occupies one of its most unusually underfilled domains. Most of all, they make the rarity more concrete. Against such an enormous scale, the few galaxies left inside do not diminish the void. They make its scarcity more precise, more measurable, and more real. Inside the Boötes Void, a galaxy does not live in the same social universe as a galaxy inside a crowded cluster or along a dense filament. Its surroundings are thinner, its near neighbours are fewer, and the chances of close gravitational encounters are reduced. This sparse setting gives the interior of the void a special scientific value. It allows astronomers to examine what a galaxy does when environmental pressure is weak. In this sense, the void acts as a natural laboratory, not because it is artificial or controlled, but because one major influence in galaxy evolution becomes less common there. That influence is the constant disturbance created by many nearby galaxies and dense surrounding structure. A galaxy is never shaped only by its own internal material. It also responds to its environment. In denser parts of the universe, galaxies may pass near one another, tug on one another through gravity, exchange or strip gas, and sometimes merge. A merger is the joining of two galaxies into one larger system, even when galaxies do not merge. Repeated close encounters can alter their shapes, stir their gas, and affect the pace at which new stars form. In rich clusters, the surrounding medium can also influence a galaxy by removing gas as it moves through hot material. All of these effects belong to environment. They do not replace a galaxy's internal history, but they can redirect it strongly. Inside a giant void, much of that external pressure is reduced. The few galaxies that remain are often widely separated. They spend long spans of time without strong interaction from many neighbours. This does not make them completely isolated in an absolute sense, but it places them in a quieter gravitational setting. A galaxy in such a region still rotates, still holds stars and gas, still feels the pull of its own dark matter, and still develops over time. What changes is the frequency and intensity of outside disturbance. The void therefore offers a clearer view of how galaxies evolve when left more nearly to themselves. This relative isolation is scientifically useful because galaxy evolution is often difficult to untangle. When astronomers observe a galaxy in a dense region, they must consider many overlapping influences. Its present shape may reflect original mass, past merger history, repeated encounters, gas removal by its environment, or several of these factors acting together. In a void, some of the more disruptive environmental processes become less common. That does not make interpretation simple, but it does reduce one set of complications. A void galaxy can therefore help reveal which features of galaxy evolution arise from internal conditions, and which depend more strongly on a crowded neighbourhood. The interior of the Boötes Void is especially valuable in this respect because the surrounding scarcity is so large. A galaxy there does not merely avoid one nearby cluster. It occupies a whole under-dense region where the broader network of matter is thin. Gas supply, gravitational influence, and the timing of interactions all depend on the larger matter field around a galaxy. In a void, that field is reduced. The galaxy grows within a quieter cosmic landscape, and this can leave visible traces in how it forms stars, how it preserves gas, and how gradually it changes shape. Astronomers often find that galaxies in low-density environments can remain rich in gas for longer than galaxies in denser surroundings. Gas matters because it is the raw material from which new stars form. If a galaxy loses much of its gas through collisions, stripping, or repeated disturbance, star formation may slow. In a quieter void environment, gas can persist more gently, allowing star formation to continue in a steadier way. It means that the path of change may be less violent and more strongly tied to the galaxy's own internal balance than to repeated outside disruption. Shape can also be influenced by this quietness. In crowded regions, mergers and close passes may distort disks, build more chaotic structures, or help transform galaxies over time. Inside a void, some galaxies can preserve calmer forms because fewer events arrive to upset them. Spiral structure, disks, and more gradual development may therefore remain easier to study in such settings. This is one reason void galaxies attract attention. Even so, isolation must not be romanticized. A void galaxy is not untouched by history. It still forms within dark matter, still experiences gravity, still turns gas into stars, and still may undergo occasional interaction with another small neighbour. The value of the void lies not in absolute purity, but in relative simplicity. The environment is thinner, not absent. That thinning is enough to make comparisons meaningful. By setting void galaxies beside galaxies from richer regions, astronomers can better judge what dense environments add, remove, or accelerate. The Boötes Void therefore serves as more than a dramatic example of emptiness. It becomes a place where environmental influence can be studied through contrast. If two galaxies have similar mass but live in very different surroundings, the differences between them may reveal how much environment matters. A galaxy in a cluster may show signs of frequent disturbance, rapid gas loss, or stronger transformation. A galaxy in a void may retain gas longer, evolve more gradually, and preserve features that crowded settings often erase or complicate. These comparisons are never perfect, because no two galaxies share identical histories, but the contrast in environment remains one of the clearest tools available for understanding galactic change. In this way, the sparse interior becomes informative rather than merely deficient. The few galaxies inside the Boötes Void are not interesting only because they are rare. They are interesting because rarity changes context. Their loneliness reduces the interference of neighbours and makes their local histories easier to interpret against the background of a large underdense region. The void turns scarcity into clarity. It strips away much of the surrounding crowd and leaves astronomers with a quieter stage on which galactic processes can be observed more cleanly. So life in a thin environment has its own scientific character. A galaxy inside the Boötes Void lives with fewer close companions, weaker environmental pressure, and a broader setting in which matter is scarce. That quietness does not stop evolution, but it changes the balance of causes, internal structure, retained gas, and long gradual development can stand out more clearly when dense surroundings are missing. The void therefore acts as a natural laboratory for galaxy evolution, not because it contains nothing, but because it contains so little around the galaxies that remain. Within the sparse interior of the Boötes Void, the most important material for the life of a galaxy is often not the stars already shining, but the gas that remains available for future change. Gas is the raw substance from which new stars form. If a galaxy keeps enough of it, star formation can continue over long periods. If the gas is lost, heated too strongly, or used up faster than it is replaced, the galaxy gradually becomes quieter. In dense regions of the universe, many outside influences can disturb this balance. In a void, the balance is shaped more gently. This makes the gas content of void galaxies one of the clearest windows into how they live and evolve. A galaxy does not turn all of its gas into stars at once. Most of its gas remains spread through wide regions, often in large rotating disks or extended clouds, and only small portions collapse into denser pockets where stars can begin to form. This process depends on gravity, temperature, motion within the gas, and the presence of earlier stars that can heat or stir the surrounding material. In a crowded cosmic environment, these internal conditions are often interrupted from the outside. Nearby galaxies may pull gas away, encounters may compress gas suddenly or scatter it. Hot surrounding material in dense regions can strip gas from a moving galaxy. In the Boötes Void, many of these disturbances are less common. A galaxy there may therefore preserve its gas in a calmer state for longer spans of time. This does not mean that star formation in the void becomes intense. Quite often the opposite is true. The surrounding universe is so thinly populated that the overall pace of growth can remain modest. A void galaxy may keep gas, but without frequent strong disturbances or abundant inflow from rich nearby structure, that gas may form stars gradually rather than in violent bursts. The result is often a quieter rhythm of evolution. New stars still appear, but they may do so in a more measured way, spread across longer time rather than concentrated in episodes of upheaval. The galaxy changes, yet its change is often patient. The gas itself can reveal this quietness. In many galaxies, gas exists in more than one condition. Some is cooler and denser, better suited for star formation. Some is warmer or more diffuse, stretched across a wider disk. The balance between these conditions affects how readily new stars can emerge. Inside the Boötes Void, the reduced frequency of major collisions and strong environmental stripping may allow a galaxy to maintain extended gas reservoirs without quickly converting or losing them. This can make the galaxy appear less exhausted than some of its counterparts in denser settings. Its star formation may continue at a low to moderate pace, even when a more crowded environment might already have driven the gas away or transformed the system more severely. This quiet behavior matters because star formation is one of the main clocks by which a galaxy's life can be read. A galaxy that rapidly uses or loses its gas tends to age in a more abrupt way. Its bright young stars fade, and the system becomes dominated by older stellar populations. A galaxy that keeps forming stars over long intervals maintains a different character. It continues to produce young blue stars, continues to recycle gas through stellar winds and supernovae, and continues to reshape itself gently from within. In the Boötes Void, this slower, steadier path may be easier to sustain for some galaxies because the outside world presses on them less often and less violently. The word quiet is useful here, but it must be used carefully. A quiet galaxy is not inactive. Stars still form. Older stars still die and return material to surrounding space. Gas still circulates through spiral arms or broader disks. Small internal instabilities still stir the system. Black holes, if present at the center, may still influence nearby gas. Quiet evolution means that the galaxy's main changes are less often forced by repeated external disruption. The system lives more by its own internal timing, and less by the constant interference of a crowded neighborhood. For astronomers, this offers a valuable contrast. When a galaxy in a dense cluster shows little gas and weak star formation, the cause may lie partly in the harsh environment around it. The galaxy may have been stripped, heated, compressed, or merged so many times that its present condition reflects external pressure as much as internal design. In a void galaxy, the same low star formation would carry a different meaning. It might reflect the galaxy's own mass, its past efficiency in using gas, or its local dark matter structure more than the force of environment. In this way, void galaxies help disentangle the many causes that shape galactic life. Some void galaxies appear to remain relatively rich in gas compared with galaxies of similar size in denser regions. This is not a universal rule, but it fits the broader picture of reduced environmental damage. If gas is not stripped away so readily, it can linger. If it lingers, star formation can continue for longer, though not necessarily at high intensity. This creates an image of gradual persistence rather than dramatic transformation. The galaxy does not race through its supply under constant outside disturbance. It draws on it slowly, and sometimes unevenly, over long spans of time. That long time scale is part of what makes quiet evolution so scientifically interesting. A galaxy in a void may preserve clues to slower modes of development that are harder to recognize in busier regions. Its structure may remain more orderly. Its gas disk may stay extended. Its stellar population may show a long, steady history rather than a sequence of abrupt interruptions. These patterns do not make void galaxies simple, but they make them readable in a different way. Their histories may be less crowded with outside interference, allowing subtler internal processes to stand out. The Boötes Void provides one of the grandest settings for this kind of study. Its sparse interior does not merely reduce the number of galaxies, it changes the conditions under which those galaxies live. Gas becomes more likely to survive in extended form. Star formation becomes more likely to proceed with restraint rather than through constant triggering and damage. Evolution becomes quieter, more stretched through time, and often more dependent on local internal balance than on repeated collision or stripping. The few galaxies that remain inside the void therefore become records of how galactic life unfolds when the surrounding universe offers little company and little disturbance. So the narrowing inward continues from simple isolation to the more intimate material of a galaxy's own future. Gas feeds stars. Stars reshape gas. In the Boötes Void, this exchange often proceeds under unusually calm conditions. The result is not a frozen galaxy, nor a place without change, but a gentler pattern of development. The sparse environment allows some galaxies to retain gas, form stars gradually, and evolve with a kind of patience that denser regions often interrupt. In that patience, the quiet interior of the void reveals one of its deepest scientific uses. At this inward stage of understanding, the Boötes Void is no longer approached mainly as a place on the map, a measured underdensity, or an environment for rare galaxies. It is approached as an idea that must be protected from false meanings. Large empty regions easily attract misunderstanding because human language is shaped by ordinary objects and familiar spaces. When a person hears the word void, The mind may imagine a hole torn through matter, a gap punched into reality, or a passage towards somewhere beyond the known world. None of these images fits the scientific meaning. The Boötes Void is a region of low matter density inside the observable universe. It is not a rupture in space, not a giant black hole, and not a doorway to anything outside the cosmos. The first misunderstanding treats the void as though it were a hole in space itself. This idea sounds vivid because the word hole belongs to everyday experience. A hole in cloth, wood, or ground implies that substance once filled the place and has then been removed. Space, however, is not like a solid sheet that can be punctured in that simple way. In cosmology, a void does not mean that space has been cut open. Space remains present throughout the region, just as it remains present everywhere else in the large-scale universe. Distances can be measured there. Light passes through there. Matter, though sparse, still exists there. A cosmic void is therefore not a missing piece of space. It is a portion of space where matter is spread thinly. This distinction matters because the fabric of space-time, the union of space and time in modern physics, is not absent from the Boötes Void. Gravity still acts across the region. The large-scale expansion of the universe still applies there. Galaxies beyond the void still send light through it. If the void were literally a torn opening in space, these ordinary physical relations would fail in some obvious way. Observations do not indicate anything of that kind. The void behaves as part of the normal cosmic landscape. Its unusual character lies in matter distribution, not in the collapse of the geometry of the universe. A second misunderstanding imagines the Boötes Void as a kind of giant black hole. This confusion arises because both ideas involve darkness and the apparent absence of visible objects, yet the two are profoundly different. A black hole is a region where matter has collapsed into an extremely compact state, producing gravity so intense that, within a certain boundary, not even light can escape. A void is nearly the opposite in large-scale character. It is not a place of extreme concentration. It is a place of extreme dilution. A black hole contains mass crowded into a very small region. The Boötes Void contains less matter than average spread across an enormous one. This difference can be stated in simpler terms. A black hole pulls strongly because its mass is packed tightly. A void exerts weaker inward pull because its mass density is low. A black hole tends to trap. A void tends to lose matter toward its surroundings. A black hole is defined by intense collapse. A void is defined by broad underdensity. Their darkness also has different meanings. A black hole is dark because light cannot escape from within its event horizon. The Boötes Void is dark mainly because relatively few luminous galaxies occupy its vast interior. Light from distant sources still crosses it freely. The two ideas therefore should not be linked except as examples of how absence and darkness can mean very different things in astronomy. A third misunderstanding imagines the void as a place outside the universe, or at least as something close to an outer edge beyond which nothing exists. This also does not fit the evidence. The Boötes Void is not beyond the universe. It is inside the observable universe as one part of its large-scale structure. Galaxies, filaments, walls, and other voids lie around it and beyond it. The region is remarkable because it is sparse, not because it occupies a final frontier. Modern cosmology does not place the Boötes Void at a boundary where the universe gives way to an exterior emptiness. It places it within the same connected cosmic web that includes denser structures elsewhere. The idea of outside can be especially misleading because human thought is trained by rooms, landscapes, and containers. A room has walls and something outside the walls. A country has borders and other lands beyond them. The universe, in cosmological description, does not work in so ordinary a way. The observable universe has limits set by light travel time and cosmic history. But a void within it is not one of those limits. It is simply a region where fewer galaxies form and remain. To stand conceptually inside the Boötes Void is still to stand within the universe, under the same laws, inside the same expanding space-time, and within the same general history of cosmic structure formation. Another false meaning comes from treating the word void as if it were the same as philosophical nothingness. In philosophy, nothingness may refer to the absence of all being, all matter, all energy, and perhaps even all structure. The Boötes Void has no such meaning. It is not nothingness. It contains space, time, gravity, dark matter in reduced concentration, thin intergalactic gas, radiation crossing through, and a small population of galaxies. Scientific language uses the word void in a narrower and more practical way. It names a low-density region in the cosmic matter field. Once that narrower meaning is kept in view, much confusion falls away. These misunderstandings often grow because the real idea is subtler than the dramatic one. A giant hole in reality sounds more vivid than a broad underdense region. A black abyss swallowing galaxies sounds more immediate than the slow gravitational evolution of cosmic structure. But science often replaces sharp dramatic pictures with quieter, accurate ones. The Boötes Void needs no violent image to remain extraordinary. Its true nature is already remarkable enough. It is a vast region where matter is unusually thin, formed through the ordinary growth of early density fluctuations under gravity across cosmic time. The correction of false meanings also helps preserve the value of the word void itself. Used carefully, the word remains useful. It tells astronomers that the region is significantly underdense compared with average cosmic structure. It conveys sparseness, not non-existence. It conveys low gravitational richness, not collapse. It conveys interior emptiness relative to surrounding walls and filaments, not an opening beyond space. Precision does not weaken wonder. It refines it. The Boötes Void becomes more intelligible and, in its own quiet way, more impressive when it is seen for what it is instead of what dramatic language tempts the mind to imagine. So this region of meaning ends with a calm separation. The Boötes Void is not a wound in the universe. It is not a giant black hole. It is not a border leading outside cosmic reality. It is not philosophical nothingness. It is a genuine but relative emptiness, a vast underdense domain within the observable universe, governed by the same laws as every other region, and shaped by the same long history of structure formation. Once these false meanings are set aside, the void stands in clearer form, not impossible, not supernatural, not broken, but sparse on an immense scale, and scientifically remarkable for that very reason. At the deepest scientific level of this journey, the Boötes Void matters not only because it is large and sparse, but because emptiness itself becomes a tool for understanding the universe. A giant void is not merely a place where less matter happens to be found. It is a region whose very deficiency allows cosmology to test its ideas about how structure forms, how gravity works across immense distances, and how the contents of the universe shape its long evolution. The value of the Boötes Void therefore lies partly in what is missing. By having less material than average, it reveals more clearly the laws that distribute matter on the larger scales. One of the first cosmological lessons drawn from such a void concerns structure formation. Modern cosmology describes the universe as growing from tiny early density variations into the vast web of clusters, filaments, walls, and sparse regions now observed. A giant void offers a demanding example of that process. If the standard picture of cosmic growth is broadly correct, then underdense regions should emerge naturally as matter gathers more strongly elsewhere. The Boötes Void becomes important because it shows this principle at extreme scale. Its existence asks not whether voids are allowed in theory, but whether theory can account for how large, how empty, and how common such regions should be across the observable universe. This makes a void valuable as a statistical test. Cosmology does not rely only on one famous empty region. It studies populations of voids, their sizes, their shapes, their distribution, and their relationship to surrounding structures. The Boötes Void stands out within that broader family because its scale is so striking. When a void of this kind appears in surveys, it becomes part of the evidence against which cosmological models are compared. A successful model must produce a universe where regions of great sparseness and regions of great richness arise together in roughly the right proportions. In this sense, the void contributes to a larger judgment about whether the general story of cosmic evolution matches the observed map. Gravity is also tested by emptiness. In dense regions, many influences overlap. Clusters contain large numbers of galaxies, hot gas, dark matter, and complicated internal motion. Such places are rich in information, but they are also crowded with interacting effects. A void offers a cleaner setting. Because the matter density is lower, the gravitational landscape can sometimes be easier to interpret on large scales. The outward flow of matter from sparse interiors toward denser boundaries reflects how gravity responds to uneven mass distribution. By studying these patterns, cosmologists can examine whether gravity on the larger scales behaves as expected within the established theory, or whether any tension appears between prediction and measurement. This does not mean that the Boötes Void by itself overturns theory or points clearly to new physics. The lesson is quieter than that. A region of such sparseness helps place pressure on cosmological ideas. It narrows what kinds of large-scale behavior remain plausible. If the universe contained many giant voids far beyond what standard models predict, that would matter. If voids moved or shaped galaxies in ways inconsistent with expected gravitational growth, that would matter as well. Even when no dramatic contradiction appears, the very agreement between observation and theory becomes meaningful. The Boötes Void then serves not as a rebellion against cosmology, but as one of the places where cosmology proves its strength or reveals the limits of its precision. Dark matter enters this inner scientific meaning as well, because galaxies form within a wider dark matter framework. A giant void is not simply a deficit of visible systems. It is a deficit in the deeper matter field that underlies structure formation. Studying the geometry and galaxy content of voids helps cosmologists infer how dark matter is distributed on the largest scales. This does not make the dark matter visible in an ordinary sense, but it helps show where its influence must be weaker and where it must gather more strongly. The Boötes Void therefore contributes indirectly to the broad mapping of the invisible matter that shapes the cosmic web. Dark energy also touches the meaning of voids. Dark energy is the name given to the unknown cause of the accelerated expansion of the universe on large scales. A void exists within that expanding background. Its growth, shape, and relation to surrounding structure may carry information about how cosmic expansion and gravitational clustering compete through time. Voids do not replace other tools used to study dark energy, yet they add a valuable angle. Because they are large, low-density regions, their evolution depends sensitively on the broad expansion history of the universe. In this way, emptiness becomes part of the evidence by which cosmology studies even the most elusive components of the cosmic inventory. Galaxy evolution also returns here. But now, as part of a larger cosmological purpose, galaxies inside a void are useful not only because they are unusual, but because they help separate local processes from the influence of environment. This strengthens cosmology by clarifying how much of the visible universe is shaped by initial conditions and how much by later surroundings. A void galaxy becomes a smaller-scale record embedded within a larger-scale test. It connects the life of one system to the architecture of the whole. There's another reason the Boötes Void matters deeply. It reminds cosmology that absence is a form of evidence. Science often advances by studying what is present: stars, spectra, clusters, radiation, motion. Yet the missing can also speak. A vast lack of galaxies across a huge volume is not a failure of observation once it is confirmed. It is a measured fact with explanatory power. The Boötes Void teaches that the universe is described not only by its bright accumulations, but also by its shortages. Richness and deficiency together define the full pattern. To ignore the empty regions would be to misunderstand how the cosmic web truly works. In this inner meaning, the Boötes Void becomes more than a curiosity. It becomes one of the cleanest expressions of a central truth in cosmology. The universe develops structure through contrast. Matter gathers here, thins there, and from that unevenness the large-scale world emerges. A giant void shows the thinning at its most dramatic. It tests the growth of structure, the action of gravity, the role of dark matter, the influence of dark energy, and the environmental setting of galaxies. It does all this not by adding a new substance or a new force, but by presenting an immense region where less is present than expected. So the deepest scientific focus settles on the use of emptiness as knowledge. The Boötes Void matters because it helps cosmology measure its own understanding against the actual architecture of the universe. It is not merely a strange absence to admire from afar. It is a quiet instrument of thought, a sparse domain through which the largest theories of matter, gravity, expansion, and structure are tested. In one of the emptiest known regions, cosmology finds not silence of meaning, but unusual clarity. Far from the crowded walls of galaxies and far from the bright habits of familiar sky-watching. The Boötes Void remains what it has been throughout this long quiet journey, not a place of broken physics, not a chamber of absolute nothingness, but a vast region where the ordinary contents of the universe grow unusually thin. Its meaning settles gently when all the larger drama falls away. Matter gathers unevenly. Gravity works patiently. Over immense time, some regions become rich and some become sparse. The Boötes Void is one of the grandest results of that simple and persistent order. Within its breadth, a few galaxies continue their slow histories. Thin gas remains. Dark matter still shapes the region in reduced measure. Light still crosses the emptiness. Nothing in the void stands outside the universe. Everything there belongs to the same cosmic law that shapes clusters, stars, and the faint glow of the distant sky. What changes is abundance. The familiar texture of the cosmic web grows quiet. The usual crowd thins. Structure becomes rare enough that absence itself begins to speak. That is perhaps the calmest truth of the void. It shows that the universe is defined not only by what it builds, but also by what it withholds. The rich and the poor, the crowded and the sparse, the bright and the faint, all belong to one pattern. The Boötes Void does not interrupt that pattern, it completes it. In one of the largest known hollows in the observable universe, the same history continues in slower and thinner form until emptiness becomes a kind of evidence and silence becomes another way of reading the sky. The great sparse region remains distant, dark, and patient. It asks for no fear and offers no final edge. It simply endures as one of the quietest rooms in the cosmic structure, wide beyond easy thought, yet fully at home in the universe that shaped it.